Hello everybody, and first of all, thank you very much for having me come and speak to you about my favourite topic. I'm extremely enthusiastic about the Apollo programme. This is because partly I grew up 10, 11, 12-year-old watching hours of coverage of men driving about, walking on the surface of the moon, doing scientific exploration, and essentially, to my young eyes, fulfilling adventure dreams like I couldn't have imagined. Quite extraordinary. And that interest has really never left me. And with the rise of the internet, I was able to express that further, and I created a website for NASA called the Apollo Flight Journal. It's an annotated transcript of the communications that happen during an Apollo mission, and I try to explain what happens. And off the back of that, I wrote this weighty tome, which I have some copies if anybody's interested. It does what it says on the tin. It tells you how Apollo flew to the moon, hopefully in nice, accessible language that any reasonably intelligent person can grasp hold of. Since then, I've done a couple of other books, co-written, one about the Lunar Rover and the Spacecraft. These are Haynes Owner's Workshop manuals. You can't really change the oil in a Gemini spacecraft, but the thought's there. And I'm working on one at present, which is an owner's workshop manual on the Saturn V moon rocket, which I'm thoroughly enjoying, and those of you with a technical bent will look forward to that. Can you come? Oh, hi there. So, first of all, a public warning. Any moon hoax believers here? I'm terribly sorry. But actually, on a more serious note, I've never actually tried to go out of my way to refute moon hoax theories directly, because what I find is that it's better just to explain how it could have happened, how it did happen in my head. Here's the technology, here's the systems, here's the procedures, this is the physics behind it, this is how it works. Go ahead and believe what you like. So I don't go out of my way to directly refute individuals and to throw up, because in my experience, a clever moon hoax believer will just keep throwing up more and more straw men to have you argue against. So, the first thing is the scale of the problem, and it's kind of like a reminder to us all of what they were trying to do. So I have my trusty globe, an 8-inch or 20-centimetre Earth, and I'm going to be, in you go, yeah. I'm going to be nasty, and I'm going to throw you a ball to catch. You come out, a wee minute. There's your Earth. You have the moon. Could you hold that at what you think is the right distance for this scale model for the moon to be with respect to the Earth? Right there? That's the common answer I get. Good. I like you because you give the common wrong answer. Right, I'll give it to you again. And if I could get you to walk backwards until I say stop. Keep going. Keep going. And I'll do. About 6 meters in this scale is Earth and Moon. In fact, it should be like, if you hold a pea out at your arm's length, that's about the size of the... That's the distance that they were going 40 odd years ago. And ever since the last crew came back in 1972, nobody has ever gone higher off the Earth than the thing. That's the scale of what they were doing and what they were achieving back in 1972. Thank you very much. I'll give the gentleman a round of applause. So, we've got an idea in our heads what they were trying to achieve. First part of it is you need a really big launch vehicle. And the Apollo Saturn V is iconic, pencil-like, sleek machine that took people to the moon. Always men. What a shame. Always men. So this is the Apollo 8 launch vehicle. As big as a frigate, as heavy as a frigate at launch, and yet this thing rose vertically off the ground and accelerated itself to orbital velocity. quite extraordinary. Every time I go to a place to do a talk, I always try to make a comparison in height. But I look at Aberdeen, and there aren't any really tall structures in Aberdeen. The best I could find is there's 20-story flats somewhere in the building. This is me looking on Google Earth. And 20 stories is somewhere to the top of the first cylindrical section. The whole thing was 36 stories tall. It's an enormous beast. But what we do have in Glasgow is we have the Glasgow Tower, the world's tallest fully rotating tower. The cupola for that just happens to be at the same height as the spacecraft on the Apollo Saturn V. So if you ever do go and visit our never working rotating tower that's never opened, and you manage to get to the top, you'll be able to have a sense of what it must have been like walking across the gangway to get into that spacecraft. The first stage was 10 metres in diameter, 2 massive tanks, 42 metres long altogether, and it flew only for about 2 minutes and 40 seconds. But during that time, it's consuming propellant at the rate of 13.4 metric tons per second. It's quite fun writing a Haynes manual at the moment all about the Saturn V, because Haynes have an association with cars, and cars have an association with Jeremy Clarkson, and Jeremy Clarkson's always talking about horsepower. Well, I like to point out that each of those 5 engines had a fuel pump. Each of those fuel pumps was rated at 53,000 horsepower, just the fuel pump. So that's my kind of Haynes Owner's Workshop manual. And the output power of this beast, when you work out the kinetic energy of the gases as they're coming out at about 2.6 up to 3 kilometres per second, 13.4 tons. If you work that out in terms of energy and in terms of power, it's 60 gigawatts. And as I say there, that just happens to be round about the peak of the UK generation consumption ability. It's quite an extraordinary output. The second stage was also 10 metres in diameter, and whereas the first stage used kerosene for brute force power, the second stage used hydrogen and liquid oxygen as their propellants, because that's much more efficient. So you get more bang for your buck when you use hydrogen and oxygen, and this is why the space shuttle also used it. So this stage added more than half of the velocity required to get an Apollo stack. Now think of an Apollo stack. When I talk about an Apollo stack, I'm talking about this lot here. 2 spacecraft. A combined weight that is about the same as a fully loaded articulated truck. 40, 45 tons, they're about 48 tons, that sort of thing. So this thing did most of the job of getting that up to speed of 7.8 kilometres per second. Very difficult development. Because it was the last of the stages to get developed, it had to take all the performance improvements. Plus, because it did most of the job, it had to take all the performance improvements. And therefore, they kept paring it back, and it kept destroying itself in the test stands. It was very, very difficult. The third stage, which was older, which was already established, 6.6 metres in diameter, it's the narrow bit, and it used liquid hydrogen and liquid oxygen, and it did the final 10% of the task of getting Apollo into Earth orbit. It then reignited to send the spacecraft to the moon, which gives it a sort of special place in the minds of those of us who like Apollo, because this was a stage that sent people somewhere, not just going round and round Earth. The later examples of these stages were carefully controlled by radio from Earth, using the spare propellant that was on board to aim them at the moon itself as part of a seismic experiment. And using the more recent Lunar Reconnaissance Orbiter, we found the impact craters for these 5 stages. The 4 stages are all together because we've known them for a few years. We found them quite quickly, because those stages were accurately tracked to the moon. But the tracking device for Apollo 16 failed, or they had lots of problems tracking it. And it's only in the last few months that somebody actually located the Apollo 16 impact site. So these are craters that are about 30 metres across, spanning across the moon's surface. And the idea was that they gave a known, understood, calibrated impact on the moon, which seismometers that had already been placed could pick up, and that was part of detecting the subsurface structure of our celestial neighbour. A very important part of the Apollo story is the Apollo 1 tragedy, 1967, when 3 men got killed 3 weeks before launch in a test. And this was the days when they used to pump up spacecraft full of oxygen at sea level pressure or more. And so the slightest thing set it off, and the three astronauts died of asphyxiation. As a result of that, they put nitrogen into the spacecraft before launch. They worked out that 40% of nitrogen was enough to reduce the flammability of the spacecraft. And then as it ascended, that air would be allowed to leak out. Fresh, pure oxygen would be allowed to go into the spacecraft, but the pressure would drop, so that by the time they got into space, the pressure would only be a third of sea level pressure, but it would be pure oxygen. So this meant that on the ground, there in the spacecraft is nitrogen, but if you're going to have the pressure inside the spacecraft suddenly drop, then you don't want to have nitrogen in your system. And so this was why they suited up and pre-breathed. So you see up and they get the helmets on, and they've got these little suitcases which are oxygen supplies, and that's getting the nitrogen purged out of their systems prior to ascending in the rocket. This is the Apollo 8 crew, and as it happened, once they've got into space and taken their suits off, they went all the way to the moon and back and never used their suits again. The suits were almost pristine. So, time for a video. So, this is the Saturn V launching. The 5 big engines at the bottom, the F1 engines, they staggered their starting points. So the centre one went first, and then the 2 pairs of outer ones went at quarter-second intervals in order to reduce the shock in the vehicle. And then off it went. In the first few seconds, it immediately began to yaw away off to one side. It was quite disconcerting to watch for the first time. And what it was doing was, just in case a gust of wind pushed it back towards the tower, or just in case one of those arms failed to retract in time, the rocket had more of a chance of not hitting it on the way up. And you can see it slightly leaning off to one side. Once it's yawed, it then rolls around to the direction it wants to go, and then all it has to do is pitch for the rest of the ascent. First stage, remember the 2 minutes and 40 seconds, that was done using what was called a dumb trajectory, a pre-programmed tilt sequence, where it wasn't trying to fly to a place, it was just changing its angle of attack according to a pre-programmed sequence in order to minimize any aerodynamic forces sideways that might tear the vehicle apart. And it wasn't until it got onto the second stage that it then says, okay, I've measured how far the winds have pushed me off. I now know where I want to get to. I'll now steer myself in order to get to the place I want to be at. I want to be at that place. After a few seconds, it hits a point where the rising speed of the rocket and the thinning air come to a maximum, and it hits MaxQ, the maximum dynamic pressure on the rocket, and it's a very dangerous point. If it gets through that, then the next thing is to stage. At the end here, the vehicle has become light, and so it's now pushing with 4 Gs, and the engines have become more efficient. And what happens is they suddenly switch them off instantly. So you've got 4 Gs on a 365-foot tower, suddenly unloads, and bang. It made the astronauts feel like they were going to hit the instrument panel in front of them, despite tied in. Lots of pyrotechnics and fireworks. There's rockets pushing the old section back. There's rockets pushing the new section forward. There's explosives going off to cut the whole thing apart. Quite a show. That's half of the entire rocket gone in length, and most of its weight. We'll go through that again. As it gets towards staging, it stops the tilt sequence because it no longer wants to have big, large metal bits rotating. So it stops the tilting, and then it cuts the whole thing apart. And away it goes. The first stage drops away. Then the next bit to go, there was a spacer ring called the interstage. very famous footage. It's become kind of iconic, and off it goes. Falls away as well, to flash into the Atlantic Ocean. And then the final thing was that the camera that's taking this itself would eject. And those cameras had little parachutes and radio transmitters on them, and somebody would go and fish them up out of the ocean and develop that film. So the third stage gets them into Earth orbit, and they have then 2 orbits, or slightly under 3 hours, to go around the Earth and just to check that everything's okay and prepare for a moment called translunar injection, which was the point when they would relight the third stage and they would head off towards the moon, once they were happy that everything was working properly. They put themselves into what was called a free return trajectory. And this is a little trick of celestial mechanics and interplanetary billiards, if you like, where you can use the gravity of a planet or a moon to alter your direction in space. You might be familiar with the Voyager probes in the 1970s. They flew past Jupiter and Saturn and used those to give them a kick onto the next planet. If you precisely align with the trailing edge of the planet, that planet will give you a gravitational kick. And this is what's happening here. To show it more accurately, what the third stage does is it puts them into a big, long elliptical orbit. The apogee of that orbit, the high point, is somewhere around about 500,000 kilometres. But it was very carefully set, its timing and its geometry was set such that as you go flying out on the outward leg, the moon is coming along and it's going to start pulling you round. And because you pass the leading edge of the moon, it takes energy out of your orbit. And in fact, what it does is it whips you all the way around and takes you straight back to Earth. So it's very safe. Not quite escape velocity. They haven't gone so fast that they're going to leave ever. Now, I've got these wee films. This is a website, phtt, that has lots of simulations. And they have this really nice one here that kind of helps to show folk who aren't maybe so familiar with how orbits work. And so the first one is an example of the Earth yellow and the moon in pink. There's the moon going around Earth. It's not quite a circular orbit, it's slightly lopsided, because that's what the moon does. Yeah, and that works a treat. So we have the idea of something moving around something else under mutual gravitational attraction. Fantastic. Our next example is what happens when our third stage, our S4B stage of the Saturn, does a big burn in order to send us away from Earth. Puts us into our long elliptical orbit. There you go. Very slow at the top end, falls back to Earth, it speeds up, and that's a standard elliptical orbit, where it's sweeping out equal areas and equal times if you imagine a line that joins the Earth. The third example combines those two. You've got the moon and you've got the spacecraft flying up. And I've timed this because it shows the free return trajectory rather well. Go. Now I happen to let this run because it's quite fun, because what happens is that my little spacecraft happens to pass the leading edge of the moon a second time, and that pulls more energy out of its orbit. So quite brutal. Had a problem, it's gone. So, this is what actually heads off to the moon, the Apollo spacecrafts. I have to say, these are toys, these are not Airfix models. And to prove it's a toy, it came with... But they are absolutely extraordinary toys. I bought these about 10 or 15 years ago. And in fact, I bought 2 sets because they were so good. And they're great, really accurate, and they split apart, which is the kind of thing you want when you're geeky, that sort of stuff. Yeah, so the Apollo spacecraft was a 4-part spacecraft, 2 in 2 parts. This is the mothership, it's the command service module. This is the bit where the conical bit at the top here is pressurized. It's where 3 men live for up to about 12 days. The cylindrical rear section is it's unpressurized. It's mostly fuel tanks and oxidizer tanks. There's 4 massive tanks in there. There's little packages for attitude control and translation when you're doing dockings. And there's 1 huge engine at the back, and this is the engine that will put you into lunar orbit, and it will send you back home again. This, the lunar module, which is a rather special spacecraft in my mind, is also in 2 parts. The bottom part has a large engine, and that's throttleable, which is very important. Throttleable under computer control mostly, and the idea is that that allows you to fly in a controlled fashion down onto the lunar surface. And then once you finish with that and those tanks are exhausted, you don't need all that weight, and so you launch back up to lunar orbit in the top half only. It has just 2 tanks, 1 there, 1 there, and that's all you need to get back up to lunar orbit and dock with your colleague. So 2 men would fly that down to the surface. 1 man stays in this here. And in fact, what they did later on was they took one of these bays at the side and they filled it with scientific instruments. The guy who stayed in lunar orbit for 3 days, he was taking very, very high resolution photographs, and he had various spectrometers and altimeters to measure the moon very, very accurately. And some of those photographs, all those photographs are now available online in 16,000 by 16,000 pixel resolution. You can download a lot. They make absolutely gorgeous posters. I have a few at home.
What's the power of the LEM engine when it's such a small thing compared with it?
It's very light.
Yeah.
The spacecraft itself is very light. It's only having to fight 1/6 gravity compared to Earth. What's the power of it? I can't give you it in kilonewtons off the top of my head. It's not very many kilonewtons. Pounds, it's something like 4,000 pounds, and I think that translates to something like 10,000. That sort of. It's a lot less than a Boeing 737 engine.
Yeah.
That way. I think the main engine there, when it's in full throttle, is about the same as a single Boeing 737 engine. I remember correctly. This is a historic piece of paper, because when they were, you would think that Apollo. Everybody associates Apollo with high tech at the time, and they were pushing the boundaries, and they were, but not in every way, because the important thing was not that something be high tech. The important thing was that something had to work. So when Mission Control wanted to send up the details of a rocket burn to the crew, it was all calculated on IBM 360 computers in Mission Control in Houston, and then it was written down on a pad of paper. PAD stood for pre-advisory data, but it was actually a pad of paper. It was one of these no carbon required. You lean nice and hard with your ballpoint pen, and it makes 6 copies altogether. And this is the actual copy that was read up to Apollo 8. It was rescued by this guy, Chuck Dietrich, who was one of the flight controllers. And what it does is all those numbers would be read up, and an astronaut would sit in the spacecraft and write those numbers into an identical form. And then that astronaut would then read all that back to Earth. And everybody would sit and tick off and make sure. And you actually see the ticks down the side. That's the ticks as the astronaut reads back all the information to make sure it's properly read up and passed back again. And what this says is things like, how heavy is the spacecraft? To what angle do you have to point this engine here to make sure that the thrust is acting through the centre of mass? What time do you start your burn? What change in velocity are you expecting the burn to have? What attitude does the spacecraft have to be in at the time with respect to the stars? All that sort of stuff. That was a level of technology that they used because it worked, because they were pilots and they were used to the challenge and response, check things off by actually speaking them over the radio. So, life aboard a spacecraft when you're flying to the moon inside one of these tiny things. Shaving was an important thing. One thing about shaving is that you don't want lots of hairs flying about, so you don't want shavers shaving systems that won't gather up the hairs. They actually spent a serious amount of money trying to invent a clockwork shaver that would keep hold of the stuff, but it didn't work very well. And what they found was the best method was to use lathered up soap and a conventional safety razor. And this is Jack Smith on Apollo 17, starting off nice and grungy after he's been on the moon, and then but they all tended to be fastidious military type. He's not a military type, he's a scientist, but they tended to be fastidious military type gentlemen who liked to look after their appearance, and so they felt good in that smelly spacecraft to have a shave. Why was the spacecraft smelly? Well, do we know what the most popular question was of astronauts when they went to... Yeah. Yes. Personal bit. Personal bit number one. What do you do with your number ones? Well, this is the Apollo 10 spacecraft that you can see in the Science Museum in London. You'll notice just below those two rocket nozzles, there are a couple of ceramic nozzles there. The one on the left, if I remember correctly, is used for urine, and the one on the right is used for wastewater that was generated during power generation. They combined hydrogen and oxygen in a fuel cell and created drinkable water, but they actually created more water than they could drink, and so they squirted what they didn't need out. Both of these were heated in order to avoid forming ice as the stuff went out. There you go, there's a picture from the film Apollo 13 of the actual thing. Unfortunately, they used the wrong nozzle. You think they'd have done their research better, but they had to be very careful when they dumped this water, whether it was urine or wastewater, because these act like little rocket thrusters. And the problem is that if you're trying to get all the way to the moon, then the tiniest little rocket thrust early on will have a profound effect on your trajectory. And so you're constantly monitoring yourself as you go, and you carefully time when you have to do these sort of things. But when all this stuff came out, first thing that happened to it was it evaporated, which caused it to cool very fast, and so it formed ice crystals, and then they became like little stars in the sky. As Wally Schirra said, Constellation Uriah. And it actually became a problem with the next part that I'm going to talk about, which is the guidance and navigation, because these little stars, created either by the fuel cells or by humans, got in the way of star sighting. Personal bit number two. Yes, sorry, I have to deal with it. Pieces were expelled into a plastic bag with sticky flanges. And then you added a germicidal sachet. You then sealed it up and you broke the sachet inside, and you give the whole thing a good knead. And then you double seal it and you stick it into a cupboard. Right, that's fine. Up to the point where you then have to depressurize the spacecraft to go out and do a spacewalk to go and get the films from the cameras that are built into the side. So they were very worried, the astronauts themselves were very worried about these bags bursting when they went outside to go and get the films. A quote from Ken Mattingly from Apollo 16. I used to want to be the first man on Mars. This has convinced me if I've got to go on Apollo, I am interested. And apparently, when they splashed down on the ocean, the first time after Apollo 8, the frogmen, the swimmers opened the hatch, they immediately smelt it and slammed the hatch shut again. So, important, how do we get to the moon? Guidance, navigation, and control. What are these things? Well, guidance is about how do you get to where you want to go? What path through space do you have to take in order to reach a destination, in this case, the moon? Navigation is how do you know where you are in the first place? Because if you're going to take that path, you have to know your starting point very accurately. And you have to keep track of that all the way along, because if you're squirting out spare water or urine, you want to know if that's taking you off your path. Control is then how do you operate your spacecraft in order to get to where you want to go. How do you operate these engines? How long for? What attitude do you have to be in order to make that work? And it's all about the state vector. If I can be drawing by my brother-in-law up there who did this. What the state vector is all about is it's 6 numbers. What you want to know is where am I and how fast am I going in 3 dimensions each. That's 6 numbers, and that set of numbers will apply to a particular time. So in this example here, if I'm throwing a stone across my back garden, I could for each instant measure how far it is from the back wall, from the fence, and from the lawn. And the next moment in time I might be able to measure, and I might be able to measure how fast it's going in each direction as well. Then if I plug those numbers into Newton's equations of motion, I can predict where that stone is going to land. And that's exactly what they did on Apollo. Guidance and navigation was all about the state vector, determining the state vector as accurately as they possibly could, and then using that to predict forward where it's going to take them. And so what they were trying to do was to measure this. They did it 2 ways. Initially they were going to do it from the spacecraft because they thought if they do it from Earth, then the Russians might jam it. And so they had procedures to do it in the spacecraft. And anyway, doing it in the spacecraft gives you a backup method of doing things in case you've got a fault. And if you do it in a spacecraft, you need 3 things. You need a computer, the famous Apollo computer that everybody says is less powerful than the digital watch. They were actually beautifully programmed, bit by bit programmed pieces of kit with about 32K of memory. And they were designed in the mid-1960s. I remember having a big micro, a BBC micro that had only 32K of memory, and that was like getting on for 15 years later. So they were quite powerful machines, and you didn't have to have screens, you didn't have to have mice and keyboards and all that sort of stuff. They had very simple mathematical jobs to do, and they were just controlling relays that then controlled engines and stuff. So they were more like embedded controllers. Next thing you had was an inertial measurement unit. This is the platform. The platform sits in constant orientation with respect to the stars, and it's mounted on a set of gimbals that allows the spacecraft to rotate around it. And you can then use that as a platform to measure acceleration dimensions. You can also use it to measure the attitude of the spacecraft with respect to that. And in order to line up this whole thing and in order to make it work, you have a set of optics. This is the Apollo 10 spacecraft in the Science Museum. And up there, there's 2 apertures. One is for a telescope, the other is for a sextant. Sextant was 28 power. And what it allowed you to do would be to align the horizon of a planet or a moon with the image of a star. So you could move the image of a star to sit on the horizon. And that told you what the angle was between the two. Just like a sextant works for a mariner on Earth. Telescope was only there to let you see the constellations. It was a wide-angle telescope. It was actually a 1-power telescope. And it was only there to make sure that you were pointing at the right star with the much more powerful sextant. And in fact, Neil Armstrong said, NASA is probably the only organisation in history that's been sold a 1-power telescope. Spacecraft navigation was a backup. Here's how it worked. If you are coasting from the Earth to the Moon, then as you coast along, if you then measure the angle between Earth's horizon and a star, that angle can only be valid at one particular time if you knew where your starting point was. And so you can mathematically work back to your position and your velocity by regularly taking sightings of stars with respect to Earth, and as you get nearer to the Moon, with respect to the Moon throughout your coast from one to the other. And so the job of one of the crew was to constantly make these determinations.
Can I just ask how accurate those?
I'll come to that in a minute. The primary method of doing this was to use radio transmitters on Earth, because they had a radio system that had a permanent uplink to the spacecraft and a permanent downlink. And the downlink was based on the uplink. So basically you had a very precise frequency going up to the spacecraft. It was altered by a known ratio and then transmitted back. And then by measuring how the frequency had changed, you then got a sense of what the radial velocity change was of the spacecraft as it was moving away from you or coming towards you. And then, of course, the telescopes themselves or the dishes themselves have to be pointed. And there's enough information in that, again, to work out the state vector. You get the distance by having a pseudo-random number, PRN, modulated into the carrier, which is sent up to the spacecraft and is sent straight back again. And then by comparing the transmitted number with the received number, and it's very specially chosen in order to reduce spectral effects, by comparing those two you could work out the delay, and that gave you distance. So you had velocity, you had distance, and you had angle, and from all that you could work out the state vector. It turned out both systems were surprisingly accurate. You could measure, they reckoned that it was accurate to about 13 metres at the distance of the moon. Quite extraordinary. And a rivalry built up between the ground and the spacecraft, because these are hotshot test pilots, and they like to show that they were just as good as those numpty engineers on the ground. And so there would be this friendly rivalry would build up between the two, where mine's as good as yours and mine's better. So they get to the moon and they're going to enter lunar orbit. And this kind of shows you the approach path that they've got. Basically what they're doing is going up and the moon's coming into their realm and they're getting pulled in by the moon. But as far as the moon's concerned, they are something coming from outside, so they're following a hyperbolic trajectory. And then what they do is they fire this engine here for about 5 minutes. And that takes the energy out of the path, slows them down, and it turns their path into a loop around the moon. Now there's a big danger here because you don't want to crash in the moon. And the problem is that once you get towards the end of your 5-minute burn, or maybe six-minute burn, every additional second of burn reduces the height that you'll have on the opposite side by 12 kilometres. And if you're aiming to get to a 110 by 110 kilometre orbit, i.e. a virtually circular orbit, then it only takes 10 seconds of overburn by your engine, and when you come round the other side, you're going to crash into the moon, auger into the surface. And so what they did was they did it in a two-stage process. Let's not do quite as much as we need to. Let's check the quality of our orbit using all our techniques. And then let's do an additional burn. Circularize it and take it to the... That's how they did it on the early Apollo missions. They modified those techniques as they got good with the later ones, and that they would insert themselves on the second burn. They would put themselves into an orbit that was only 17 kilometres above the surface. But they were getting really good at controlling. And then they come to land on the moon. Landing on the moon was computer controlled. It's actually interesting to discover that landing on the moon was the only thing that they had to do where they had to have a computer. They could do everything else on an Apollo flight without using an onboard computer, because they could do all the navigation based on Earth if they wanted. Everything could be done. It wouldn't be very friendly, it wouldn't be very safe because it wouldn't have so many backup systems. But the only thing where a computer was absolutely necessary on board was the landing, and that is because they have only as much propellant as they need. They can't afford to carry much more than they need, and so therefore it has to fly a near optimal trajectory from orbit down to the surface. So this was done using 3 computer programs in the machine called P63, P64 and P66. P63 was basically just to slow them down, get them down to a certain speed. It's also aiming for a certain point above the surface called high Vade. So they're flying like that. What's that?
P65.
P65, no, P65 wasn't. P65 was land automatically. But we're talking about hotshot test pilots here, and they prefer to land manually. And it's not actually true manual, it's kind of kid-on manual, but I could discuss that later. Yeah, So they're flying along like that there, engines blasting out, it's slowing them down, and that's P63. And then what happens is as the landing site gets near, they go to P64, and it turns into more of a helicopter. Then once they get near, they then go into this semi-manual mode, where the commander has control of attitude, and that means he can aim the thrust of this just by doing that there. The computer is still in control of their sink rate, how fast they're going down, but he can change that. He can increment it up and down in order to help him effect a good landing. Low gate was only about 100 metres. High gate, 4 kilometres, something like that sort of height. And P64 between high gate and low gate was very interesting because the windows on this picture here, this is a recreation that was made for the cover of a very good book about Apollo. The window that the commander was looking out of had painted lines on the outside and on the inside. The idea was that if Neil Armstrong or whoever moved their head to the right place, then those two sets of lines superimposed. And therefore the computer would output numbers, and those numbers would be relevant. And so the computer would be able to say 40 degrees. The computer would also yaw the entire spacecraft from side to side to make that line up with where it was taking them, and it would give them this number that would tell them how far to look down the line, and that's the way the computer indicated to the commander where it was going to land them. And then he could use his stick to say, oh, I want to go a wee bit to the left, click. I want to go a wee bit down, click. And it would redesignate its planned landing point at that point. And unfortunately, what they show there is that Armstrong was coming up to a crater called West, surrounded by a boulder field, and he decided he didn't want to land there, so he goes on, and you'll see that in our next little film. This is speeded up. We're in P63 at the moment. All of a sudden it'll go into P64 and you'll see it suddenly tip forward. And it tips forward. So that's the computer tipping that forward. He's now looking to West Crater. You can actually see it ever so slightly. It's just bobbing in and out. And Armstrong can see that. But you see how the whole thing is kind of moving quite juddery. They had huge problems with slosh in the tanks. The fuel was sloshing all over the place. So he sees that he's getting taken towards a boulder field, and we'll see the boulder field in a second. And so he changes to P66 and decides, stuff that, I'm going to fly on. So there you go, P66, and he tips forward to keep his forward velocity going, flies over the boulders, now in control of the attitude, and he can tell the computer how fast to let him down. And now he pulls back, slows himself down and gets himself down. This little crater here he would walk up to later. It's 60 metres away from the landing site. Now he's blowing up some dust. Dust's getting blown. And interestingly, that lunar dust was getting blown away so fast by the engine plume that some of those particles will have gone into orbit around the moon. That's what I thought. Because the moon's speed is only 1.6 kilometres per second. Yeah.
Right, only had a few seconds of fuel left at the end.
There's a complicated story there. See how I mentioned slosh? The slosh caused the sensor to be uncovered early. Started the clock early. And when they landed, there was still 20 seconds left in that clock. And it's reckoned there was probably at least another 20, 30, 40 seconds. But it had been realised that this sloshing fuel had fooled them. Not as simple to say, oh, they only had so many seconds of fuel. Their best measurements told them that, but that's not strictly true. So, this was the destination.
On those,
Sorry?
on the
Yep.
sloshing of fuel.
They didn't have time to modify Apollo 12. Is that right? No, Apollo 12 they tried to retro-modify. They, like a ship in a bottle sort of thing. They had a fold out that they could put it into the tank, fold it out, and it was all these baffles that they tried to put in, but it only partly helped, and it wasn't that effective, and so they still had big slosh problems on Apollo 12. By Apollo 14, they had long enough time in order to properly redesign the tanks and the problem completely. So this was the destination. Run through some landing sites. This is Apollo 11, a flat area. They didn't want any slopes, any mountains in the way, keep it simple. Same thing happened for Apollo 12, except because they had overshot Apollo 11's planned landing site by 6 kilometres, they wanted to go for a pinpoint landing site, and so they chose the Surveyor 3 probe that had landed 31 months earlier. And they were very successful. And they also had a trick by measuring the velocity as they came around the moon, and then feeding a number up to the spacecraft, to having worked out what the error was in their flight path. They then put a number in to fool the computer to landing them where they wanted. Very nice. Apollo 13 was the successful failure. You'll all have seen the movie, I guess. This is a photograph you don't often see, but that's the service module with its blown out side panel. The moon's in the far distance. The command module that is still dead at this point, it hasn't been powered up, is here. Apollo 14, they tried to go to Cone Crater. That's Cone Crater up there. It's 370 metres in diameter. And the reason they wanted to get to Cone Crater was that craters on the moon serve as very, very handy drill holes for geologists. Because the physics of crater formation, basically point explosions, the physics of that means that if you collect samples from the very rim of the crater, they are the deepest samples that have been scooped up by the impact. And then as you sample radially away from the rim, you're sampling shallower and shallower samples. And they wanted to sample the rim, the ejecta bed there, which they reckon was from the creation of the man in the moon's left eye, the Imbrian basin. So they walked up to this crater. That's the view of it as they were landing. They got within 30 metres of the rim. They thought they were lost. They could still see the lunar module way down the plane, but they were trying to get to the rim and be able to look over the edge of the rim, but the shape of the landscape failed them. Apollo 15 went to a truly majestic place called Hadley. This is Hadley Rill on the left. It's a channel about 1.3 kilometres wide, 300 metres deep. A former lava channel. So 3-point-something billion years ago, lava used to flow along there. And in the distance is a mountain. Anybody guess at the height of that mountain? Oh, there's always someone who goes over the top. Because most folks say like a few hundred feet or something like that. That's fine. It's 14,000 feet, about 4.5 kilometres, I believe. But the thing about the moon is there's nothing to tell you. There's no snow line, tree line, there's no fading off into the distance because there's no atmosphere to degrade the view as you go further. So it's very, very difficult.
Quite far away.
Quite far away and quite high. Yeah. It's like the Alps, it's the height of Alps. The best of the Alps. And by Apollo 15, they had a little car to drive about on, which completely transformed the exploration because now they could go for multiple scientific objectives. And on Apollo 15, what they were trying to do was that they thought mountains will provide rocks that represent the original lunar crust. And they were saying to me, if you can find a little white crystalline rock, we think that's part of the original lunar crust. And they were successful. They found a rock that is made of a mineral called plagioclase, called anorthosite because it's more than 90% plagioclase, and it's part of the original lunar crust. Very beat up, but they can date it back to more than 4 billion years old. Apollo 16 was sent to a place called Descartes, and what they were trying to do was they were trying to find where, instead of all the dark bits of the moon are volcanic, all the dark splodges, those are great sea lane almost of fluid lava that flowed over and solidified. But they wondered whether there was volcanics in the highlands that didn't have this dark basalt lava, and so they went there to find it, and what they found was actually it was just lots of ejected debris from some great ancient impact. So theories were overturned on Apollo 16, very important. Apollo 17, the final flight, was sent to this amazing valley with 10,000 foot mountains on either side, a very beautiful place. And one of the reasons they went there was to visit this crater called Shorty. It's on the right hand side there. And what they found was orange soil. Hoping that this crater had a dark halo around it when seen from orbit. And they thought maybe that's recent volcanics on the moon, so the moon's heat engine was still working. But when they got there, they got this orange soil, they were very excited, they took it back home, and it was discovered to be 3 billion year old fire fountains, titanium rich glass that had spewed up hundreds of kilometres into the lunar sky and then fallen down. And then an impact crater had excavated this stuff and created a dark halo. Very interesting. I love lunar geology. So we're departing the moon, we're leaving it. And as I was saying earlier, there were cameras, modified spy cameras actually built into the side of the service module. And this is a sequence of photographs taken of the moon as it departs. Now it turns out that the moon is orbiting the Earth at a speed of 1 kilometre per second. Almost exactly 1 kilometre per second, it so happens. And so basically when Apollo wanted to return home, all they did was, if the moon's going that way, I suppose for you guys it's that way, if the moon's going that way, then they fired the engine to make them go the opposite way by 1 kilometre per second. So that essentially what happened was, with respect to the Earth, they came to a dead stop and the moon moved out from underneath them, fall to Earth, which is a good way to think about what they were trying to do, get back to Earth. It's basically stop your motion with respect to Earth, the moon slides out from under and you fall back. That's the far side of the moon. Then as they come further and further away and start to fall to Earth, you begin to see near side features like the Sea of Crisis there, and then you see fertility and the Sea of Fertility start to appear as you see more and more of the front side of the moon. And on the way home there were a couple of interesting astronomical events happened. Apollo 12, they thought this was the most spectacular part of their entire mission, which was 4 hours from landing, they coasted through Earth's shadow. And they had no colour film left except for colour movie film. So this is a frame taken from their movie camera, 16mm camera. And basically what you get is you get 40,000 kilometres of sunrise and sunset all the way around the Earth because the light bends around the edge. And once the sun had completely gone from view, they had an Earth that was illuminated by a full moon behind them. They could see the clouds, and they could see the lightning storms, and they could see the city lights in India and such like. They found it to be incredibly spectacular, and not something anybody had expected or thought of. They knew they were going to go into the dark, because it was marked on their flight plan, but nobody thought to say, oh, by the way, take a look and see what you see. Wow, this is amazing, and they filmed it as best they could. Another interesting one was Apollo 15. When they came home from the moon then promptly went into Earth's shadow after about 2 days. The spacecraft was midway between the moon and Earth, but the moon had moved off and into the shadow, and so the spacecraft had this very unusual view of a lunar eclipse from the side. There are 3 very poor quality photographs there that don't show very much, but what you do get from it is that the curve of the Earth projected onto the moon, but seen from the side, enhances that curve or cancels out that curve depending on which side it's on. It was a total eclipse of, well, that's it. I think after, as it was going in, that's the moon entering Earth's shadow, and that's it coming out or something like that. The next job is to get back home, re-enter Earth's atmosphere and get onto the surface of the ocean. And that required re-entry, which was not easy because when they went into orbit, they were doing 7.8 kilometres per second, because that's the speed you need, that's the speed the ISS is going at in order to stay up there. Then go on to the moon, you have to increase your speed. to 11 kilometers per second. That's light. 11 kilometers in 1 second is quite something. And when you come back home, you then got to lose all that speed. Moreover, if you go into Earth's atmosphere, you've got to make sure that you lose more than enough speed so as not to get below orbital speed, to get below 7.8 kilometers per second. Otherwise, if you find yourself going back out, you're going to go into orbit. And by this time, by the time they enter, they have got rid of that part. And this is all that's left. All tank of oxygen, there's a handful of batteries, and it will last for about 3 hours. It's only going to take them 15 minutes to get onto the ground, about half an hour from when they disconnect. If they find themselves going into Earth orbit, with just that there, then they're essentially dead men. So the trick was to have a path that came back from the moon, but it was deliberately set such that its perigee distance was only 40 kilometres. And something that approaches Earth with a perigee of only 40 kilometres is bound to enter the atmosphere, and so therefore it's bound to slow down. But there's a possibility it might then go through the atmosphere and come back out the other side. These things were not symmetrical. Things were heavy on one side, deliberately so. What that did was that when they hit the atmosphere, they naturally adopted an attitude to the airflow that was lopsided, and they essentially could fly. And so merely by rolling the spacecraft around, you could fly in this direction. That way you could make yourself go higher, or turn it around, you could force yourself lower. So just by rolling the spacecraft, you could actually fly yourself to where you want it to go. The computer knows where the ships are. The computer knows where it is because of the whole guidance system on board. And so it basically sat and flew the whole thing through the atmosphere, constantly turning the spacecraft round and round in order to aim for the ships. And the idea is that if you dig down, you'll hit denser atmosphere more early, which will slow you down even more. But you don't want to dig down too fast because you increase the pulse on the spacecraft, and you also increase the G load on the astronauts, and you get it too deep, damaging. Equally, if you try and fly up a wee bit, you'll tend to be in the thinner parts of the atmosphere, and so therefore you'll slow down less, and if you do that too much, you'll end up sailing right through the atmosphere and coming out the other side and find yourself in orbit for 3 hours or more. So the trick they used to protect themselves is called ablation, where they covered the heat shield of this with what was essentially epoxy resin, araldite if you like, a phenolic resin, which was injected into, they had a fiberglass honeycomb, and they injected all the cells of that fiberglass honeycomb with what was essentially araldite. And what that does is it charges, so when they hit the atmosphere at 11 kilometers per second, they compress the air. And they deliberately have this blunt thing because that forces the air to be compressed a few centimeters away from the surface. So the shock wave is not directly touching the spacecraft, but instead the shock wave is slightly set off. The spacecraft is still feeling the heat from that shock wave because the shock wave is like the temperature of the sun. It's thousands of degrees. But this phenolic resin chars and burns away piece by piece. So they allow that heat shield to get eroded away by the very high temperatures of the shock wave. And by the fact that it's not actually touching the spacecraft at the time means that it will withstand a certain heat pulse as they come through. So they used 3 programs, a bit like landing on the moon. They had program 63, yet again, but this time for the command module. And what it did was it sensed when the drag was 1/20th of a G. Detected the 20th of a G drag. It then started the monitoring systems. It says, right, here we go, we're going to steer you through the atmosphere. Next, program 64 concentrated on flying the thing, turning it around, in order to get their speed to less than orbital speed, so that they could guarantee that if they went back out, which they might, because sometimes they had to fly out in order to extend their flight, if they did that, they would be doing it at less than orbital speed, and so therefore they were bound to come back into the atmosphere. And then the final part, well, there was an intermediate P65, P66, which was for the skip out. Because if they chose to skip out, and Apollo 11 had to do it to avoid a storm, if they skipped back out, which they now did at less than orbital speed, they could then control the skip back in. They had program 65 and 6 to do that. And then program 67 was the one that did most of the steering. It's concentrating on getting to the ships. And in fact, they got so good at it that the ships stopped sighting themselves at the target point because they were scared that the spacecraft were actually going to hit the ships. And so they would deliberately offset the ship by a few kilometres. And here's a little film. Shows the re-entry. And so what you're seeing is the plasma, the ionized air glowing. It was like being on the inside of a fluorescent tube as they came in. But you can see the horizon of Earth rolling around as the spacecraft steers itself. Thoughts that I've put together to show you this idea of how the spacecraft, the computer's doing the flying here. Nobody flew these things in. Did all the work. And then they pop the parachutes. First thing that comes off is the very top of the spacecraft, the cover. That reveals the parachutes. Flies away, pulled away by its own wee parachute. Then out come two drogue chutes. They are to stabilise the thing, slow it down and stabilise it, so that when mains come out, 3 pilot chutes come flying out, and they will pull the 3 big mains parachutes. There go the 3 big parachutes. Also known as Tunnock's tea cakes. And splash in the ocean. The problem they had then was that this was no boat. This could float in the water like that, but it could just as easily float in the water like that. Stable 1 or stable 2. And unfortunately, Apollo 12, what happened with them is that it hangs from the parachutes kind of like that. Now, if you hit a wave that away, you get a nice toe in, and that slows you down in a nice, gentle fashion. But if the wave happens to be like that when you hit, you get a hefty thump. And that's what happened on Apollo 12. It hit the wave the wrong way. And the camera that had been used to film one of those films that shows you outside, that camera came flying off and hit the guy in the head and knocked him unconscious. But he was supposed to pull a circuit breaker in order to energize the system that would allow them to disconnect the parachutes. He's unconscious. His commander's over on the other side yelling at him to pull the breakers, or to push the breakers, and he couldn't do it. So eventually Apollo 12 got pulled over by the parachutes. And so that's Apollo 12 being righted back up the right way. Apollo 15, what they found was as they come down, they get rid of all the very nasty rocket propellants that are stored in the tanks around the edge here. And there was a slight bias towards the fuel of Apollo 15s. And so there's lots of unburnt fuel in it, and it's nasty corrosive stuff. And it caused one of the parachutes to fail. That parachute began to stream. Luckily, the spacecraft was designed, or the parachute system was designed to drop the spacecraft down safely. The third parachute was a kind of safety factor, and they needed it in that case. So here's the poor chap on the right with the plaster across his eye and 6 stitches. That's the Apollo 12 crew. And this is Apollo 8 on the surface. Now, you see pictures of these when they're on flight, they're very silvery. They're silvery because very thin silvered mylar film has been glued to the surface of the epoxy. But they thought that, you know, when they designed it, they thought that this heat shield would be. But what they found was that only the base got it. The top, the mylar was still sticking to it, and people would peel off little strips of mylar to keep as souvenirs from the craft. They were barely singed. So that's his back home. Thank you very much. So I'll happily take any questions, although there was a good pile of questions throughout, but any questions? Yes, sir.
Those different programs, were those all kept in the memory through the flight, or did the
Very good question. The Apollo spacecraft used a computer memory technology called core rope. It was basically, you had little ferrite cores, little toroids, and magnetized in a certain direction. And then there were wires fed through them. Depending on which way the wire threaded through, that gave you a 1 or a 0. In fact, a single core could be used multiple times to give you ones different times. Lots and lots of planes of these. That was non-volatile memory. It was actually very good for environment because it would 38K actually, to be honest. In fact, when I say 38K, that's at 15-bit words.
All those different programs were.
All those programs were pre-loaded, and in fact there was a huge bureaucracy after the flights, in fact during the flights, as to what programs got on there, what functions do you actually want, what do we need, what would we like, and there was a huge bureaucracy had to be put in place and what programs were going to be allowed. Programs were gently modified as they gained operational experience and they wanted to do more complicated. And they had 2K of volatile core, ferrite core memory, which is wired in a different way, and you can change the polarity of the magnetic field of those wee cores. And so it was possible for mission control to feed up numbers that were essential. We talked about the attitude of the spacecraft. What attitude is the spacecraft adopting in space? And it only knows that because it's measuring it with respect to that platform. But then the question is, well, what way is that platform itself oriented in space? It had a definition with respect to the stars. It was called RefSmart, reference to a stable member matrix. That was a set of numbers that would tell the computer and tell the platform, once you know 2 stars, here's how you have to orient your platform. And those numbers were radio linked directly into the. That's where the state vectors were kept as well and things like that. Yes, sir?
Can you remind us what went wrong on Apollo 13? How did that impact the mission?
It's a long story, but I'll try and do it quickly. I did it quickly, and they got it wrong. They said there was a broken coil. 1965, the spacecraft itself was designed to work at 28 volts. The batteries and such like were 28 volts and what have you. So it was a 28 volt system. And so contractors started building things for 28. Then they decided that, well, at the Cape, at Kennedy Space Center, where it's at the launch tower, we're going to use 65 volts. So a message went out to all the contractors who then passed that to all the subcontractors saying, change everything to be 65 volt compatible. That failed to get to a subcontractor for subcontractor. That failed to get to the people who were making it. Now, so there were all these oxygen tanks being built. They were like flasks. They held extremely high pressure oxygen, extremely cold, and they had heaters in them so that as they drew off oxygen, they could restore the pressure, the supply pressure, by turning on heaters. That would heat up the oxygen, that would restore it. But they had safety thermostats to stop the heaters beyond. Now, Apollo 10 had one of these tanks, and they decided to take it out for some reason. When they took it out of the spacecraft, they dropped it 2 inches. By dropping it, they damaged the little tube. Worked okay, seemed to work not too bad, and so they kept it, and it eventually got installed on Apollo 13. Now, move forward to when Apollo 13 was doing its tests 2 or 3 weeks before launch. Demonstration test, where they do the entire thing of fueling the whole vehicle. The only thing they don't do is ignite the engines to actually launch. They do. Therefore, they filled this tank with Did the rehearsal, all went well, right into the tanks. So an engineer had the bright idea of, well, turn the heaters on. The heaters will heat up and it will force the stuff out. And so they sat the technician, watch that meter there, make sure it doesn't go over Fahrenheit. But unfortunately the meter only actually went to 80 degrees. Anyway, he sat and watched it. It went to 80 degrees. But what had happened was that the heaters had actually made it too hot inside the tank. The thermostat had tried to throw. But unfortunately, because it was 28 volts, not 65 volts capable, it welded itself shut. On, and it took the temperature inside that tank up to about 500 degrees centigrade. All the wiring, which was made of Teflon, that all became brittle, charred, what have you. And they did the same thing again a few days later. That same process and did it. So now you've got this auction tank with these wires leading to some fans, because they use fans to stir up the stuff and to homogenize it and stop it separating. These wires have got their insulation damaged, often places and such like. And every so often during the flight, they ask to stir the tanks, because the capacitance probe is trying to measure the capacitance between. When they switched on the fan, the wires came in contact are in a high pressure pure oxygen. PSI. Fire went up, started consuming everything.
But you said the smallest amount.
Yeah, it threw them, well, they were quite near the moon by that time. It did throw them off course, but by that time they weren't altitude above the moon. Fly around the back of the moon at quite a height. Did a short deliberately slightly off in return. And they did another burn as they were coming back in order to speed them up, so that the Earth would do one turn less and they would get home earlier. And they were also aiming at the back of the lunar module. It's not shown that it is there. Cask. That cask is full of plutonium. It's there to power the experiments that were going to be installed on the surface. They didn't want that plutonium falling into the ocean just anywhere. So they deliberately timed this burn that was going to send it back. Earth would rotate the right amount such that that thing there would re-enter there. Plutonium was kept in a cask made out of graphite that had been specially designed. It's all intertwined, intermingled. The planning for an Apollo mission was massive planning meetings that they had in order to sort of Apollo mission. Never mind. they had to dive pretty deep. Yes, sir.
So was all the oxygen with the
Good question. The auction for the two spacecraft. This spacecraft had two big auction tanks, big spherical auction tanks, the tanks I've just been talking about, one of which blew up. And that auction was for two purposes. One of them was to feed oxygen to the astronauts, and the other was to combine with a tank of hydrogen and make electricity. Now, they breathe out, and as they breathe out, they generate carbon dioxide. So the cabin air is becoming more and more saturated with carbon dioxide unless you do something about it. And so they use canisters of lithium hydroxide to scrub the carbon dioxide out of it. Absorbs the lithium hydroxide, it absorbs the carbon dioxide out of the air. And then after a while that canister gets used up and they would put a fresh one in. And so they had worked out that they had enough canisters to get to the moon and back. And then what's left is pure oxygen again, and that just gets recycled. The spacecraft leaked deliberately, i.e. they didn't mind that it leaked a wee bit, and so what they did was they knew that with the leak rate that they had enough oxygen in the tank to constantly keep it topped up all the time. Yes, sir?
Did they have one on Mars?
Yes, they did. In fact, that's an interesting topic. Right in front of the guy who's sitting in the left seat, which is the captain's seat, and normally be the commander, but it was the command module pilot who would fly it during re-entry. Right in front of him was a device called the entry monitor system. This was entirely separate to the spacecraft's own guidance and navigation system. There, so that the pilot could make sure that the guidance and navigation system was doing the proper job. And the way it worked was that there was a screen, a little window about 4 inches by 4 inches. And that little window had a mylar scroll. That scroll was driven by an electric motor, such that it moved across the screen according to how their speed fell. So it was set to a specific speed, 36,000 feet per second, 11 kilometers per second, and as they slowed down, it moved according to how far they had slowed down. And on the vertical axis, there was a little scribe drawing, and it was drawing the g-force. And there were lines on the graph that kind of guided them towards the g-forces that they should expect at that time. So that if the guidance navigation system failed, the pilot could grab hold of a stick, and he could do the turning in order to keep forces within an acceptable corridor as it was drawn along that entry monitor system mylar scroll.
Prior to that,
On Apollo 13. On Apollo 13, the command module, that bit there was powered down and cold. They powered most of this down as well. But when you power this back up, one of the things you can do is you can use the optics on the back to point at 2 stars. You point the sextant at 1 star and then point it at another star. And in fact, I was amazed when I got a decent Meade telescope in 2004, and it's got a computer in it, and you point at a star, and then you point at another star, and it knows the whole universe. And that is exactly what the command module pilots were doing when they were lining up the guidance platform, the guidance system inside Apollo.
so did they power it up?
They powered it up a couple of hours away from Earth. That was the only time, that guidance system had been powered down since the explosion, and they had to power it up to be able to fly in the atmosphere. Now, the lunar module is still live. They kept the radio on, and mission control were monitoring the thing as they came in. And what happened there was that they saw that their trajectory was shallowing, i.e. they were coming to Earth, and instead of coming in at a certain angle, that angle was becoming a bit shallower, i.e. the perigee was getting a wee bit higher. And so they had to do a short burn. It's shown in the movie as if they were flying all over the place, but they had to do a short burn in order to adjust that to bring back their angle of approach to the mountain. So yes, they did a course correction as they were. That was based on Earth tracking, yes.
And the F1 engines, the
Yeah.
main engines, the plans were thrown out.
If they have been, then I don't know what I'm going to do.
Oh, sorry, they were misplaced for you.
No, that's a myth. That's a myth. Lots and lots of paperwork will have, I could well imagine, had been chucked out at the end of the Apollo. But all the important paperwork seemed to have gone to the National Archives and Records Administration, something like that.
That's the Russians.
That's the Russians. And in fact, I mean, rocket technology moved on. We don't build rocket engines that way anymore because we have computer-controlled lathes. They were kind of hand-sculpted almost. They were hand-welded. Those are really quite remarkable. But there are better ways to build engines. Like printing nowadays, we do 3D printing as one of the parts for rocket engines. Amazing. So it wouldn't really matter that much whether you had the blueprints or not, because nobody's going to build it. In fact, we just buy from the Russians because they build it. Yes?
I was just going to ask.
Yep.
At any point, did he start swearing and losing it a bit, or?
There's a famous section in Apollo 10 where they start talking about a turd floating by.
Fair enough. No one's getting stressed or.
And you can read in Apollo 15. Apollo 15 had Descartes was the commander, and he was kind of very controlling. Al Worden was quite laconic, quite sarcastic, and Jim Irwin was a very religious gent and very much under the shadow of Descartes, and he did exactly what he was told. He was a good boy. And you can kind of see when you read the transcripts, not the main transcripts, the communication with Earth, but the transcripts of the onboard recordings, because they had onboard recorders, they had little tape recorders going, and sometimes they went for perfectly good reasons, and they also happened to have a soundtrack on them that were mostly there to pick up. But with some of the transcripts of that, you can see Al Worden taking the piss out of Jim. Winding him up, yeah. Yeah. Anything else? Yes?
Yeah, on the, when I used to watch this as a kid, we must be the same age actually,
Yeah,
about 10
I'm
or
56.
6. Yeah, and when the Saturn V took off, I could never quite figure out why it just simply toppled over. The main engines are on gimbals, aren't they?
They are. Not all of them.
Controlled.
Not all of them. No. Yeah, so 10 metres across, you have 5 engines. The central engine is fixed, it cannot move. 4 outer engines are gimbal mounted, and they can move about 5 degrees, plus or minus 5 degrees from the centre line, under control of the computer. So you've got this massive thrust, like the equivalent of a 690-ton building weighing on top of you. That's the thrust of a Saturn V. One of those engines, 690 tons equivalent, is the force that those things are doing. They are controlling the angle of them with supreme precision by the computer. So those 4 outer engines were used to control the attitude of the vehicle as they rose off the pad. So as it's rising up, the thing is going, oh, I'm going to be a bit this way, I'm going to be a bit that way, and so it's constantly steering those engines.
You see them moving, can't you? When they light up, you see them.
You saw the shuttle engines do that, but you don't see them do that.
Okay, right.
You can see them do it during the tests, because they have various tests, and you see them moving all the engines in various ways. But the interesting thing is that this bottom bit where it says USA, that's basically a big kerosene tank. Massive kerosene tank. And above that is 1,500 tons of liquid oxygen. The centre of gravity of this 360-foot, 110-metre tower is quite down near the bottom. And you've got these engines going in the thing as it's going up. And so the astronauts, they're on the end of a very long lever. And the way they describe it is, it's like a rickety old freight train going down a bad track, because they're constantly being thrown from side to side as the engines are constantly being gimbaled in order to keep them from falling over. Because it's like balancing a pencil on the end of your finger. You've got to keep this thing upright. And so there's an inertial measuring unit up in the 3rd stage. Above the 3rd stage there's an instrument unit. It's a ring. It's about 1 metre tall, and it contains one of these gimbal platforms. It's measuring their position. Therefore, it's able to say, oh, I don't want to follow over this way or that way, I want to go this certain course. And so the engines are constantly being driven in a servo loop in order to take them on the course that was desired, and that's why it doesn't fall over. Because they couldn't get the raw power. The best engine they could build at the time had £20,000, sorry, 200 thrust. But to get that whole assemblage off the ground, you needed £7.5 million of thrust. So they didn't need efficiency at the start. What they needed was raw power. And what you get from kerosene is extremely concentrated raw power. So it doesn't have to be particularly efficient. And you still find SpaceX with their current rockets are completely kerosene. There's no hydrogen power on them at all. They do the whole thing. So NASA got into a thing where, oh, we want the best, we want the very best. Tendency for them. They like the high energy aspect of hydrogen. Certainly argue that because the Saturn V was marginal to get Apollo to the moon, that had they not used hydrogen for the Yes, sir.
The third stage.
Some of them are still out there.
Did those arrive at the moon before they landed, or
It arrived around about the same time as they arrived at the moon vicinity. They would then go into orbit around the moon and spend a day or so. It crashed at roughly the same time as they. Some of those stages didn't crash on the moon. The early ones were sent into solar orbit. And in 2003 there was an asteroid spotted. Correctly. And it appeared to be in the Earth-Moon system. We seem to have an actual satellite. And then people studied its orbit a bit more carefully, and they realised it was probably captured. Reckoned that it probably left the Earth-Moon system in 1971. Oh, that'll be either Apollo 15, oh no, that one was impacted. Apollo 14, no, that was impacted as well. They looked at it with spectroscopes and they discovered that its surface was titanium oxide. Quickly, this wasn't an ordinary asteroid. Worked out that it was most likely Apollo 12's Saturn S4B. Still out there, along with Apollo 10s, Apollo 11s, Apollo 8s, and Apollo 9s as well. Yes, sir. Go on. Yeah. No, I didn't say that. What I said was the mission lasted up to 12 days.
Oh. What were
18? The command module pilot, he was the guy most concerned with the systems. He spent an awful lot of his time just systems monitoring, checking things over, studying tanks, making sure that things were running as they should. And they did a fair amount of science. So it was mostly housekeeping. There was housekeeping of that spacecraft. There's a saying within people who study Apollo where they say that Apollo was an example of 21st century exploration carried out with 1960s technology. And part of that was that in order to make it happen, everything was marginal, everything was only just working, everything was right on the edge of what we could do at the time with the technology that we had in the 1960s. And so there was an awful lot of having, things weren't automated very much. There was an awful lot of having to do things manually, look after things, check the values, check that things weren't changing more than they ought to. A regular job that had to be done was to purge the fuel cells. The fuel cells, they put hydrogen and oxygen past a catalyst, and that made power. And unfortunately, impurities like argon and such like that were in those gases would clog up the pores, and so every so often they would have to flush those to restore their operation. So they were looking after the thing all the time, kind of kept them busy there and back. Plus they had various chores to do, like corrections. They had 4 opportunities for mid-course corrections on the way to the moon, and 3 back. And every time you fire an engine in space, you're putting your life in danger, because if that doesn't fire up at the right time in the right direction, you may not have enough fuel to get yourself on a path back to Earth. And so as one of the astronauts said, every time they come to fire an engine, it's sweaty palms time, gentlemen. Questions, folks? Yes, go on.
What was the politics behind it? Because how could Kennedy have said, we'll do it in 10 years? Was he advised
He was advised,
that it's doable in 10 years?
by some very optimistic engineers.
Well, but they did it in 10
And given the time where they had been trounced by the Soviet Union, wanted desperately to have a reply, and they thought if they do something like a space station, something that was relatively easy to do, it would be easy for Soviets with their very powerful rockets to be able to upstage. They wanted something that was more complex, have a longer lead time, that would give them time to be able to develop that technology and jump ahead in terms of themselves, and to show the world, especially the Soviets, that that level, if you want to look at it. And the engineers had by that time already been looking at what would it take to get to the moon, so they already had some ideas on paper, and they were given enough money and given certain developments in technology. By 1967, they thought, and so give ourselves a bit more time, and actually others went. Most engineers were apparently aghast. Half years. There you go. Yes, sir.
And would you be scientific value in putting
Is there scientific? The point of spaceflight in my head is not science. The point of spaceflight is to extend the human realm, to take ourselves further away, like moving out of Africa, moving across the world, making ourselves a multi-planet species. It's kind of what humans do, perhaps, you could argue, but science is not the reason for doing it. If all you want is science, send your robot probes out there and get them to do it, because they'll do the science a lot cheaper and a lot safer. But if you want to something that is wonderful for the human spirit,
What's the future now? When are the Chinese preparing something, or is about mining the moon?
Helium-3, I think, is a non-starter.
Sorry?
It's a non-starter, I think. The guy I showed you who's shaving, Jack Schmidt, Harrison Schmidt, he was the only scientist to go to the moon. And he's a geologist, and he has studied very intensively, and he's written a paper, and it became a book, and I bought the book and read it, where he proposes that we do a big push in order to strip mine parts of the moon to extract helium-3, because a cupful of helium-3 will run the United States for 4 days. It's like, woof, amazing stuff. It's, if you could extract it, it's probably the most valuable material per gram that there is. Unfortunately, we can't get fusion to work with the easiest of components, deuterium and tritium. It should be relatively easy to get fusion to work with those, and we can't get it to work yet in a way that generates vast amounts of power for our civilization. And we know that the reaction to get helium-3 fusion to work is way more difficult, a lot more difficult. So I'm very dubious about the amount of investment that would be required to start strip mining the moon, and also to get helium-3 fusion to work. If it does work, great, because it produces protons, and protons are direct electricity, rather than generating neutrons, which blast all over your reactor and make it radioactive and nasty. So if it works, it would be great, but the problem is it's very, very, very difficult to get it. Probably not where to put our... Chinese have got... They're taking their time. They're slowly working their way up to it. Good on them. I like Elon Musk. Heard of Elon Musk? Elon Musk is this American entrepreneur. He started up companies. One of them makes an electric car that trounces just about every other car on the planet, called the Tesla. He has another company called SpaceX, which is trying to rapidly, massively reduce the cost of spaceflight. Because the thing that makes spaceflight very, very expensive is that every time you send a rocket up, you then dump it in the Atlantic Ocean.
Is it the man who invented?
Yes.
He was on television, yes?
He's on television a lot, yes,
Yeah.
because the things that he's been doing are becoming really interesting now. More particularly where last month he managed to send a pile of satellites into orbit, and he got his first stage back. Nobody else has ever done that. That's a game changer. If he can do that reliably, he will cut the cost of orbital access by at least an order of magnitude, if not more. That's a game changer. All bets are off after that.